This video, I've set up a game where I have a turtle and these purple blobs that fall. And I'm going to pretend these purple blobs, let's say, are turtle food. And when the blob hits the turtle, I'd like the turtle to grow. Um, you could imagine all kinds of different similar things for a game. All right, so the turtle food code here, I've got a function that builds the food object. Um, and what I've set up is this function draws the food object. It checks if the food is off the screen. Once it falls off the screen, it just disappears. We use remove to get rid of the object entirely. And then it's going to check, is the food touching the turtle? And if it is, the turtle will eat the food and then remove it. And down here, I've got my turtle object. I'll give the turtle an eat food method, which will just make the turtle target width multiply by 5%. So my turtle will get 5% bigger each time it eats food. That will be very exciting. All right. What this tutorial is about is how do I draw a function that checks, is the piece of food touching the turtle? So a version of that problem is called collision detection. We could abstract that out in any number of ways, but we'll start with a simple version where we're just going to ask, is this blob of food touching this turtle? And we'll do the collision detection a pretty straightforward way. So here's some graph paper describing our situation. Now, the food is defined as a perfect shape. So it has a center point, which we know is labeled x, y, right? So it's got two coordinates that we know about. The turtle, on the other hand, is a little bit more complicated. It's drawn in terms of, oops, let's come back here. The turtle is drawn, with a x, y in the top left corner and a target width and a target height. So now what I need to do is figure out, are these two things touching? We're going to be doing some kind of estimation of that. If you got really into this game, you could potentially do something where you'd essentially go through every single pixel of the turtle, ask what color it is, and then check if it's within range of the XY coordinate. But of course, that's going to be pretty expensive. That's going to be the computer doing a lot of different calculations. So what we'd like to do is come up with something simpler. And for this first little approximation, we'll do the simplest thing. So I'm going to say, let's imagine there's a center of the turtle here, and the center of this circle here. And let's think of this turtle as being something like a circle. So we could decide what that circle is. What we might do is just take if width or height is bigger. The way I drew this, you'll notice it goes taller because I have the width taller than the height. I don't know if that's true for the turtle or not. We could check. So we could just take whichever one's bigger, draw the circle around it, and check if they're touching. If you would rather potentially have the ball able to like pass through the turtle's head, you could instead draw the smaller circle, right? That would be another option. But we're going to just imagine one of the circles. Why are we doing that? Because checking if two circles collide is actually really simple math. In that case, we want to get, instead of the, we want to get what we might call CX and CY, which is to say the center of the turtle and the center of the center point instead of the corner point, right? We'll check that center point. We get its radius, and then we check the two radii. So if we know two radiuses between two circles generically, we can always check if the radiuses are touching by checking the distance between the 2 points. if the distance between the 2 points is less than the sum of the radii, then the 2 circles are overlapping, because there's no way to draw 2 circles with those radii closer where they won't be touching. Doesn't matter where you put the circles, right? Any way you orient the circles, if we check the distance between the radii and it's the distance between is smaller than the sum of the radii, they must be overlapping. So, of course, in this case, it would be possible to, for example, take this red circle and slot it in right there and have it not actually touching the turtle, right? So there'll be like a collision circle around the turtle that we're going to check, and that's how we'll do the math. The distance formula you've probably seen. If you haven't seen it, Googling it quickly shows here distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. That's really just another way to spell the Pythagorean theorem, because the internet will provide. We're just looking at a triangle, right? So here's a graph that will show us relatively nicely. So the distance between the two y coordinates is the sort of upright side of the triangle, or the vertical side. Distance between the two x coordinates is the horizontal side. We know a squared plus b squared equals c squared. In this case, distance is c, and we subtract and get our distance. So that's the simplest way to do this. So in our case, we've got x2, x1. We can actually, instead of thinking so abstractly, we'll think of that as the turtle. So we'll take the turtle.y. So if I come back here, now the turtle.y is not going to be, so I'll call it, well, cy is going to be turtle.y plus turtle.target height over 2. Remember, we have to adjust cx equals turtle.x plus turtle.target height over 2. We're going to treat it like it's one big circle. I guess, well, I should do the target width. We'll go to the actual center of it. All right, so there we've got it. So now the turtle radius is going to be equal to the whatever's bigger target width, turtle target height. Math.max is a function which just gives us the bigger of the arguments back. I think that's how math.max works. I could check the console. Math.max 7.2. Yep, that's what math.max does. Very good. Okay, beautiful. And then the x and y of this item we already have. So instead of, we can think of the height of the triangle, oops, do constants here, is equal to this.y minus cy, right? Const width of triangle is equal to this.x minus cx. It doesn't matter if these are negative or positive because we're going to square them, because that's the beauty of the Pythagorean theorem. Distance equals math.square root is just sqrt. And then now to do squares, we'll do math.pow. It's a function which takes the item and then the power. So we're going to say width of triangle to the second power, or squared, math.pow height of triangle to the second power, or squared. We take the square root of all that, and that's the distance. Beautiful. So now the last thing we have to do is check if the distance is less than the sum of the radii. So is it touching the turtle? So if distance is less than or equal to this dot size, that's the one radius, as we call that the size, plus turtle radius. I got that there. Return true, else return false. And I can just throw a log statement on so I can see if it hits. The likelihood this works the first time is astonishingly small, and I've already gotten error. Okay, I just made a typo in width of triangle. Now I've got a turtle. Oops. Looks like I made it disappear. Did we get a hit? We did get a hit. And a little note, I've got some old log statements here I really should have gotten rid of. Okay, I went through and took those out. Those are from the last tutorial when I had the angles wrong. But now, if I make enough of these, we should see console log a hit every time one of these things hits the turtle. Hit, there it goes. It's going to hit some more. Hit, 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 hit. And we can see my turtle is growing. That's the code I made, is for it to grow each time. It seems to be hitting a little too soon. So something may be a little wrong with my code. And it'd be worth doing a little bit of investigating to see what I did wrong. It may just be that the radius of this drawing is too far off. All right, I will go ahead and write some log statements to see what's going on. All right, I have found the bug. I had a comma here instead of a plus. So rather than saying the square root of a squared plus b squared, I was just saying the square root of a squared. In JavaScript, if you hand a function more arguments than it expects, it doesn't complain. One of my many frustrations with that feature is this kind of bug is a little harder to find than it would be in most languages. That said, while I was trying to find the bug, I actually built a whole debugging infrastructure, which you can see it work here, and I'll just talk you through that because it could be useful to think about. What I did is I used the drawing functions to sort of show how the drawing was working. So I drew the circle around the turtle so I could see the circle that I was drawing. And then I also drew a line between the two. And when they hit, I display the radius. Right now, when they hit, I have it just freezing the circle so that I can see it. And doing this kind of thing is a good idea. So for example, maybe instead of doing the maximum, I should do the minimum. That makes a slightly smaller turtle circle. In this case, because it's actually a set drawing, it's not a general thing, but it's specific of the turtle, I might now start fiddling with the numbers to say, you know what, that's about 10% too big, so let me try making it 80% of minimum size and see, oh, you know what, even smaller. Let's try even smaller than that and see how that looks. Oh yeah, that looks closer. 70%. So what about 66%? And I can just sit here and fiddle with those numbers. Having the actual circle drawn makes it possible for me to see that. So what I did is I just added here, I passed my isTouching a context object, and I went ahead and drew the circle. So that's my little debug circle, so I can see what's going on. Makes it a lot easier to troubleshoot. Maybe I want to go even smaller, 0.6, and I can see, does that look okay at all the rotations? It does, and here it is. So it would be tempting to get rid of all this stuff. What I might do here is just add a default debug argument to the turtle food. And then rather than get rid of all this stuff, I can just put it in an if statement so that if later on something's funny is going on in my game, I can see all that again. So now that debug stuff is gone. Oops, most of it's gone. I should have added it to wherever all those text got written. So here's the text, so I could add here if this debug, add that. All right, and now, of course, my turtle behavior. can be here fixed. So maybe, again, I could say if not debug, we eat the food and we remove. So now, rather than deleting all my debugging code, I kept my debugging code. It's gone. It's not doing anything right now. Oops. This was part of the debug code. All this stuff. Alrighty. Let's pretty up my JavaScript. Lovely. Alright, so now I don't draw those silly little lines again. Oops, I seem to have still made the turtle grind to a halt by mistake. Let's take a look at where that happened. Oh, I didn't say not this.debug, sorry. No. Oh, that's not if not debug, that's if debug. My mistake. And then this is the else. Sorry. Let me get that logic straight. So if it's in debug mode, we stop these things. If it's not in the debug mode, we eat the food and we remove the food. So let's see the food disappear. There we go. Now the food disappears, and the turtle should grow each time it hits food. There we can see our turtle slowly getting bigger. And I now have my turtle successfully eating the food and getting bigger. Very nice. All right, so that's an example of working collision code. Surprisingly easy to get wrong. That was the simplest way we could do a collision. That was just two circles colliding. The other ways to think through collisions, instead of thinking about two circles colliding, it'd be easy to think about two rectangles colliding. So, oops. If you think about rectangles, they're defined by a width and a height. And there are essentially 4 points that you have to check. So if you have two rectangles that are in line with your grid, that's a pretty easy problem. It's just a bunch of less than or greater than statements to ask each point, is it inside of the other rectangle? So if any point is in the other rectangle, which you could check by saying, is it greater than this x but less than this x and greater than this y but less than this y? If that's true, then the rectangles intersect. That only works for straight rectangles. If you have more complicated shapes, like even let's say you've got one rotated rectangle and another rectangle, the easiest way to think that through is actually as a generalizable series of polygons or lines. And then we actually have to do some more basic math. So if you have a series of points, you can think of those as lines, which you could put into slope-intercept form, y equals mx plus b. Given 2 points, you can find the y equals mx plus b line. Given 2 lines, you can find the intersection. So you basically just do the algebra to find the intersection of 2 lines. And then you check, is that intersection in the range between those 2 points? If it is, then the two polygons are colliding. So depending on how complicated your polygon was, let's say that you had a 5-shaped polygon, and then, your turtle might be a 15-point polygon or something. You would have to check, 15 lines, and these 5 lines, and if any of those lines intersect, you have a collision. That's a pretty good way to do this. It takes a little more algebra, and I'll let you work that out on your own, or I could help you with it, but I checked with your math teachers, and they say that getting a slope-intercept formula out of 2 points is something that should be within range of all high schoolers. And once you can do that, this is really pretty straightforward. All right, I'll leave this to you. Good luck.